So hi, I'm Yash, and this recitation is all going to be about debugging neural networks and visualizing neural networks to hopefully help you debug code or to select better models and such. So we really need this session to be super interactive because we can learn only if debugging skills if you ask me enough questions about why particular errors occur so that you don't have those errors in the future. And I hope that you all can all pick up some skills so that you all don't face as many errors, you can finish your part 2s on time and such. Okay. Of course, if anything doesn't make sense at any time, please feel free to stop us. We have a lot of time. We don't have an infinite amount of slides. We can definitely stop and talk more over here than as compared to lectures. Yeah, okay. Is it changing? Oh yeah. Okay. So far, you all have learned what neural networks are and what they do. Can someone give me some examples of where neural networks are used? Just raise your hand and then speak. No one knows what neural networks do? Okay, sure, yeah, go ahead.
Computer vision.
Sure, computer vision. Someone else?
ASR.
Yes, automatic speech recognition. Anyone else? Yep, so for generative modeling. So neural networks are being used in a bunch of different ways today. As we heard, computer vision, ASR, generative modeling, and a bunch of other domains. So in your lectures, weeks 2 to 4, you all learned how to train neural networks. Quickly, can anyone tell me what the main algorithm is, the training algorithm that we use to train neural networks? What is it called? Backprop. Yeah, backprop. Okay. In the previous recitations, you all have learned how to define models in PyTorch, how to optimize these models, add things like batch norm, and other things that hopefully make your model like faster or better or some kind of optimizations. So, and hopefully all of you all have at least started homework 1, part 2. I mean, if not, then really, well, you all have more guts than I do. And the recitations, when you see the recitation code, at times you might think that, oh man, this is just 150 lines or 200 lines of code. I could write this easily, like in a couple of days. Writing code for neural networks and debugging the code is much harder than what the recitations make you think, at least. And I'm sure you all have all been through this. Can I have a quick show of hands of who all has passed the A cutoff for homework 1 part 2 so far? Right. We have 2 people in the house out of like 15. Okay, great. So I hope that some of these tricks will help you all pass this cutoff in next 2 days. I think you all have like today and tomorrow. Okay, let's go ahead. So in general, in computer science, debugging is like a super important skill. But in deep learning, like this skill is even more essential because you really don't know where you've messed up in most of the cases. Most of the times, you know, I'll have like people coming to the office and saying like, I have a big model, it doesn't work. My friend has the same big model, it gets 80% accuracy, my model 10%. Help me. I mean, and then like I'll look at the code, you'll tell me my code is rock solid. Everyone, when they come to office hours, they're like, my code is rock solid, there's no fault with my code. And I'll look at your code, it probably looks good. But the accuracy that you have is terrible. And you know, you have all of these sort of weird errors that you don't know how to catch. So hopefully, we can break down how these errors are caused, what their root causes are, and how we can write better codes so that we don't face these errors in the future. Yeah. So one of the main reasons why debugging in deep learning is even harder than debugging in computer science in general, which in itself is pretty hard, is because there are so many different ways in which errors can be caused. So you can have some different Python-based errors, you can have PyTorch-based errors, math-based errors. You can read the list from there. There's a bunch of different errors. Can someone quickly give me an example of what a Python-based error might be? Just a guess about what you all think it might be. Anyone? How many of you all have all written efficient data loaders on your first attempt, like an O of 1 data loader? So you all, yeah, like looking at the class, like, yeah, it seems, yeah. So this is what you might classify as something of a sort of, it's hard to like classify them exactly, but maybe this would be more of a Python-based error. A PyTorch-based error, like, okay, like you figure out finally that your data loader works fine, but your model still takes 3 hours to train. Any guesses why? If your data loader is like working in constant time, all of your other code seems fine, and your model is training, but it takes 3 hours to train for a single epoch. Any guesses about what a common cause might be? Anyone?
Updating the model parameters properly.
It's possible, yes, you're not updating the model parameters. Say you realize that the per iteration time that you're taking is very, very, very low. Like normally you read posts on Piazza, people are saying my neural network trains in 20 minutes, and you run the same code and it takes you 3 hours. Any like guesses? Any other guesses, common causes? There we go, GPU, right? Your model may not be on CUDA, or your data may not be on CUDA or something of the sort. If your model is on, your CPU is on like RAM and it's not in the GPU, your model is going to take forever to train. And it's very hard sometimes to catch these things because you think that you've transferred your model to the device because you have those .2 statements and such. But you really need to go in and ensure whether they're working in the way that you think they're working. Okay. Yeah. Okay. So the plan for today is to essentially give you some general tips on how to organize your code. Maybe we can go through some of the basic forms of errors that you all have, and in general how you can debug all of these sort of errors. Then towards the end, we're going to talk about some techniques to basically visualize how your learning process is going through. And maybe you can like learn a bunch of new things about how to compare different models very easily. Like you don't have to look into the terminal and like always like then scroll up and try to find the point at which you had the best accuracy, find the model, find that particular checkpoint, and you have like 500 different runs with different hyperparameters. How do you figure out which was the best particular one? So these are all tricks, tips and tricks that will be covered in the visualization section. And yeah, please apply these before coming to office hours, especially for part 2 and onwards, because the part 2s are about to get a lot harder. Like, so it would be a lot easier for us if you all could like implement all these things. Okay. So one of the most general coding tips that we are going to cover, the one that will help you the most is that you should write modular code. Can anyone tell me what modular code is over here? Someone? Yeah. So for those of you who didn't hear over here or from the other campuses, his answer was when you split code into easily separable segments, and usually like each block of code that you separate it into has a very different and specific functionality. So one of the big advantages that writing modular code gives you is you can write tests to check whether each part of your code works exactly the way you want it to or not. Okay, so the way you want to write your modular code is that suppose you have your data loader, right? You have your own dataset class. You write your own dataset class, and within that class or within that file, you should have stuff related only to the dataset. You don't want to be setting some other hyperparameters there or doing any kind of other stuff. Say you have a file where you define your model. That's all you should have there. You shouldn't have your training loop over there and some other stuff over there within that function or within that file. The reason this helps you, right, is at the end of the day when you go to test your code and if the TA tells you or you feel that okay, there's an issue in your data loader, you can very quickly try to essentially run through the data loader and check okay, like, am I getting the right shapes out of this data loader? Are the samples that I see correct? Is the data being shuffled properly and all these things? These are things you can test easily when you have modular code. Okay. Any ideas on how you could like test or check the model architecture? I'm sure like you all must have tried at times, but you can't say you don't want to look at your code. You want to check whether the model that you're training is the right one. Any way to just find out what your model architecture is? Exactly, there you go. They are very simple things. You just literally print the model. And if you have an nn.sequential model, it will give you a very beautiful view of what your first layer is, what your second layer is, and so on and so forth. And once you see the entire model, you can very easily find out is this the exact kind of architecture that I was planning on using? Or is this the architecture that I was planning on using 3 experiments ago, but I forgot to switch a variable name or something of the sort? So this is something that you should always print your model architecture before you start your training loop. And you should ensure that this is exactly like what you expect it to be. Because at the end of 10 hours of training and wasting infinite amount of money on AWS, you don't want to find out that you were training the wrong model altogether. Okay. So yeah. So some other examples of why having modular code might help you is suppose you want to just test the data set. You can very quickly like just iterate through the data set and make sure the shapes of all of the elements that that you get from the data set or the data loader are what you expect them to be. Another one could be to figure out, and this is like a fairly common error, especially with homework 1 part 2. It is to see whether your inputs and your labels are aligned. So in homework 1 part 2, we have utterances. Within each utterance, we have variable number of frames, and each frame has 40 features, right? And then you sit and either concatenate them or write some awesome cumulative distributive function sort of thing, and then you do a binary search on it to try to get the current element quickly. In doing this whole game, if you index the y label and the x label incorrectly, in the sense that they are not aligned with each other, your model is going to learn garbage. And it's not going to have great training accuracy at all. And at best, what it will do is it will just start predicting the most common labels. Like you'll see a bunch of people, their models are just learning the label 108 or one of like the really popular ones. Your model is like, I don't understand anything from the input, but I know that the most probable output label is 108, so let me just predict that on every occasion. So there are reasons why your model behaves in the way it behaves. Another, so once again, do not write the dataset model or the training loop and just throw them all together and pray to God that they work. That's not the way we write code. We want to test each and every one independently and make sure that they work independently, and then ideally they should work well when you combine them together. Yes, sure.
Yeah, I have a question with respect to the model. When we create the model, is there any particular difference between the sequential way of doing it through the loop, or rather kind of writing layer by layer? Is that like kind of you use one some type of problems and
Yep.
use another one?
Yeah, so the question for the guys from the other campuses is that, is there any difference between using nn.sequential and just defining your layers independently and then just doing a forward pass through them? And to answer your question, no, there is no difference. But when you want to start writing more complex code and you want to start writing more complex forward passes, when you'll see for homework 2 onwards, you have things called skip connections. And those are a bit harder to do when you have sequential models. When you want to bifurcate your output in between, or you want to branch the output out in between, sequential won't let you do that very easily. But the power that nn.sequential gives you is that you don't have to explicitly write the forward pass for each and every one of the different layers in there. You literally just take all of your layers, dump them into nn.sequential, you just call a forward pass on that, and PyTorch does some magic at the back end and it ends up working. So it abstracts a lot of the redundant code that you want to write, but when you want to have more functionality later, like you want to do more complicated things with your code, nn.sequential won't be good enough then. And you'll see this in homework 2 part 2 onwards. Yeah. Okay. So coming to centralizing hyperparameters. Okay. How many of you all are doing the following? Just let me know. You have a data loader, right above it you define batch size. You have the optimizer, right above it you define the learning rate. And wherever you define weight, wherever you're using weight decay, right above it you define the weight decay parameter. We have a bunch of hyperparameters here, and inevitably we end up writing this super ugly looking code where all of your hyperparameters either lie in different files or different parts of one file. And don't look at me as if you all have never done this. I have done this as well. I know most people have. And it's really important that you stop doing this. And there are a bunch of reasons why we don't want to do this. So before I get to the reasons about why we don't want to do this, I want to tell you all some ways in which we can easily fix this. An easy way to do this, a super easy way, is you just have a file called config.py. In config.py, you literally have all of your, the only thing you have in that file is you have a variable called batch size and the corresponding batch size, a variable called learning rate and the corresponding learning rate, a variable called activation and then the activation function that you want to use, and all of the other hyperparameters that you possibly would want to tune in the future. Some people can go so far as to even specifying the model architecture over there in a list. So what does this give you? This gives you a very, it makes debugging very easy in the sense that I remember in a bunch of homeworks, what I used to do was I would define the batch size multiple times in different locations in the code, and while running the code, you never know what batch size you're running at that point of time. Or say you want to iterate through different learning rates or something. If you mess up one of these hyperparameters or it is not what you think it is, you end up wasting so much time trying to figure out what the error is that it is really not worth it. Besides, this gives you the advantage of having really clean code. And yeah, I mean, clean code is nice to look at, nice for the TAs to look at. So definitely that's something that you should be doing. In the scenario, say you're super adamant and you say, I won't create a new config file. Okay, then at least please define all of your hyperparameters at one location in the same file. Don't have them at different locations in the same file or in different files or something of the sort. Another thing that people often do, which is also super useful, is to pass hyperparameters as command line arguments. So you can use Python modules like argparse, and you can just Google Python command line arguments. And in that manner, you can very easily just from the command line itself tell the program what learning rate you want to use or what batch size you want to use and all these different hyperparameters. Okay. How many of you all, and please raise your hand with this, started your first model with a 4 or 5 layer model and you found out it didn't work? Anyone here? There, we have one truthful person in the house. So inevitably, what happens is you gain a lot of confidence from the recitations and looking at the code, and you're like, this looks easy enough, let me just implement a big model, and you keep it to train and you're like, this will train well, I have confidence. And you look at it at the end of 8 hours, and again, it's at random accuracy, it's at 1 or 2% accuracy. This shouldn't happen with you. We don't want to waste too much time in the beginning having big models that don't work. We want to start with small models that don't work. I mean, they're not going to work in the beginning anyway. Might as well start with something small where you can iterate quickly. Once your model starts working, you can slowly start increasing the number of layers. And if you don't have much experience with neural networks, you might feel, oh, I don't know how many layers to add. I don't know how many neurons to have in each layer. In fact, I remember when I was doing this homework in the last semester, I felt like I was doing gradient descent in my mind on the model architecture. I wasn't able to figure out what are the heuristics for this. How do I possibly define a good model? So the way you do it, what I learned was that you start with a small model and just keep increasing a couple of layers at a time and make sure nothing is breaking in between. You cannot have a 2-layer model and jump to a 12-layer model directly and hope that everything will work out in between unless you have enough experience, because turns out in most of the cases maybe you need a higher learning rate, maybe you need to regularize your model more, There are a bunch of different things that happen in between, so it's better if you can iterate through models. And when you iterate through models, I don't mean you need to train them up to the very end and waste all of your AWS credits. Train them for a couple of epochs to try to understand what the training dynamics are like and what you should expect for the next version of your model. Yeah. Okay. So, so these are some of the common forms of error. You have like coding errors, and this is essentially when your code or your model doesn't do what you want it to do, broadly speaking. Training errors are when your model does what you want it to do, but it's kind of crap at it. And testing or decoding error, this is not something you'll normally face in this homework. It's when your model trains well, you know your model has good accuracy on the training and validation set, yet somehow it sucks on the testing set, or maybe you don't have a great decoding scheme, but this is a topic for later discussion. So, yeah. So as the slides say, you should check for coding errors first, and then training errors, and then testing errors. So yeah, so we're going to go through some of what the common errors are and how we can try to spot them. So coding errors. So signs that you may have a coding error, and I'll be surprised if there's any one of you all who hasn't had a single one of these errors, which would be pretty cool actually. But say your loss doesn't, you start training your neural network, the loss doesn't decrease at all. It's probably a coding error. You check, you trained your model and it always prints the label 108. Like, what's up with that? That's probably a coding error. And then like, okay, like training stops in between, or training takes forever, or you try to do some augmentation of the data set, or you try to normalize your data set and you ran out of memory. These are all like sort of coding errors. I'm sure you all have faced more coding errors. Are there any like basic coding errors that you all faced? So maybe I can like talk about them later. Anyone? And you all are great coders. Like no more coding errors here. Okay. Okay. So these are like some of the main coding errors. And so how do we fix these coding errors? Now this is one of the most important slides. I want you all to understand this very well. So the idea is that you either want to use PDB or you want to use print statements to print everything from where you start from where you think the errors are starting. And you want to be very methodical in the sense you don't want to skip over any of these steps, and you want to do each of these steps very well. So one of the common things is it's very hard to tell which one of these things is happening if your model is not working well. So you need to test all of them. So very often what happens is you have your data, right? It's not iterating. You go to your data loader and you figure out that, oh wait, in the dataset class, my get item was returning things from a constant index, or you were using some complicated hash map or something to get values for the current index, and the hash map had the wrong entries in it. You want to make sure, and so you can diagnose this symptom very easily by printing out the data at every iteration in the training loop. Make sure it's not the same. Another thing you want to do is you want to make sure you're iterating over the whole training data set and that you're not leaving out any samples. So a very quick way of doing that is to keep counting the number of samples that you've seen. You just keep adding by the batch size at each iteration to make sure that you've seen the entire training data set at the end. Another pretty common one that I talked about earlier is instance label misalignment, where your input data and your output data are not aligned, and then your model starts predicting garbage. Okay, shape errors. These are like super common. So one of the common shape errors that you would possibly face in this homework is, suppose you had zero context while doing homework 1 part 2, and so you have a 40-dimensional vector that you pass through your neural network and it tries to predict something out of it. And now you try to take k frames context from the left, k from the right, you concatenated them together, and you just returned it. Can anyone see the problem in this? I just slice the utterance, taking k frames to the left and k to the right. I slice them together and I return this. Can anyone see the shape error that I will have? this is all I do. Yeah, sure, go ahead, Roman. Oh no, it's you. Yeah.
Oh no, I was just thinking.
Oh, okay, sure. Okay, you can go ahead. Exactly, you need to flatten it, right? Your input to the neural network is expected to be a single dimensional vector for each sample. You need to make sure that you flatten this vector before passing it in. And the thing is, right, the error sometime will seem super weird. PyTorch will give you 100 lines of errors and it will tell you shape mismatch, this, that, and you feel like really you've done something terrible. But at the end of the day, like most of it is just function calls one to another. You need to go to the very end and it will tell you exactly what sort of error you are facing over there. And if it's a shape error, it's very likely that your input is not in the format that your model expects it to be. Again, like another common form of shape error is that if you did homework 1 part 1, the cross entropy loss over there expects your data to be one hot encoded. PyTorch doesn't expect one hot encoding. PyTorch only wants the particular labels. So if you try to pass a one hot encoded vector to it, PyTorch will throw some super ugly warning. I don't remember what it was. It says something you can't have multiple classes or something of the sort. So yeah, you need to be sure that the data that you're passing into your model right before your forward pass is exactly the right shape that you want it to be, and it has exactly the right things you want it to have. So another important thing with this is another easy way to debug this is you just turn your shuffle equal to off on your data loader and you print out the first batch from your data loader and you manually inspect those first few elements from your dataset class. Make sure they're exactly the same. In that way, you can make sure that you're not skipping over any particular elements and that there's no misalignment. Is there a question back there?
Yeah, you just mentioned that, I mean, the input should be like a one-dimensional vector. But I saw that there are some like neural network that, for example, the computer version, and then you would take like a three-dimensional.
That's right. That's right. So what I meant was more in the context of homework 1 part 2. When you're running, when you're using an MLP expects a single dimensional input. And later you'll see that we can definitely have MLPs that expect two-dimensional inputs and so on. Like, and I'm not sure that will be covered, but the idea was I was talking about homework 1 part 2. Yeah. Okay. Again, hyperparameters. Ideally, if you have followed what I said in the previous slides, you have your hyperparameters in a config file. You shouldn't have any problems with the hyperparameters. But just to be safe, it doesn't cost you anything to print them out right before your training starts. Print them out, print out the model summary, print out the hyperparameters, make sure they are exactly what you want them to be. And again, we don't want to find out at the end of the training that our hyperparameters were something wrong. Okay. Many times, okay, you did all this and you can't figure out, like, your model still doesn't train, you still have a very low loss. So one way of diagnosing whether your model is learning anything at all is to print out your parameters at different iterations. You can literally access the weight and the bias components of the linear layers by just doing .weight and .bias. And once you do that, you can just print out their contents at each training iteration. So if you feel that maybe my model is not learning anything, you can actually test whether it's not learning anything at all to see whether gradient descent is even working in this case or not. Many times what happens is you've forgotten one of the steps in between, because of which the parameters are not updating. Okay. One more thing I'd like to stress on is that it's essential that you do all of these things on your local machine before running them on AWS. Or if you're doing it on AWS, do it on the T2 micro first. We don't have an infinite amount of compute resources. And as you saw the post on the other day, once you run out of resources, we can't help you. You're on your own over there. Yeah. Okay. So time issues. So this is a specific case of a coding error when your model works but things are too slow. So a very quick way to test out to find out which part of your code is slow is to use a time module. You can use the time module to basically time how much time it takes for the data loader to fetch items, for how much time it takes to do the forward pass, and how much time it takes to do the backward pass. Many times the time module will not give you an accurate representation of how much time it's taking the data loader to do things, because the data loader, when you set the number of workers to something greater than like 1 or 4, it'll start fetching things in the background. But you'll know when your code is slow, you'll know that your code is slow and it's taking forever to train. Yeah, and once you can find the particular part of your code that is performing slow by using the time module, you can try to fix it. One thing that I want you all to make sure for all of the future homeworks is you're going to be writing data set classes for everything. Try your best to have the getItem function run in constant time. The data loader is the single biggest bottleneck that you can have because of writing inefficient code. The bottleneck that you want to have is the backward pass, is the backprop part of your code. You don't want the bottleneck to be in the data loader. Your model will take forever to train if that is the case. Okay, so what are some quick ways that you can make sure that which you can speed your code up? One obvious one is to run your model on CUDA. But say your model is on CUDA and your code still takes forever, and you found out that your data loader works fine, right? So there could be a bunch of other reasons why this is still happening. Maybe you're calling some sort of weird function in between, or there's some part of your code that's like you're looping over the same instance multiple times, or something of the sort. So you see this printout over there. How many of you all recognize what that is? How do I get that printout? Please just raise your hands. How many of you all recognize how to see that thing? Okay. For the rest of you all, it's super important to know where that came from. That is from the command NVIDIA-SMI. This lets you see what your current GPU utilization is in terms of the amount of memory and the percentage utilization. This is the single most important command that you need to figure out whether your model is running on CUDA and whether it's utilizing the CUDA resources well. If your model is not, so as you can see, this model currently is using 738 megabytes, maybe just a small model. The important number you want to look out for is volatile GPU utilization. We want this to be as close to 100% as possible. This means that for most of the times your GPU is being fully used and it's doing lots of extensive computation here. Even if you have something 60 to 70% and above, it's good. The minute this is at 30% and below, you have some inefficiencies in your data loader, and the inefficiency doesn't lie in your model training. Also, if your model somehow isn't on CUDA, it won't be taking up any memory here, and right below this I've cut the screenshot of. It will also tell you which processes are using this amount of memory. You need to make sure that your training process is the one that's using this memory, and again make sure that the GPU utilization is high. Okay, yeah. So yeah, if you figure out from this previous slide, say you saw that your GPU utilization is high, your memory usage is high, you're still having timing issues, make sure that, once again, just make sure that your data loader is running in constant time. Yeah, another common thing that I've seen for some reason is that on some distributions of either Ubuntu or Linux or some other distributions, just using .2 device doesn't work very well, and you feel like, well, I did .2 CUDA and that doesn't work. A thing you can try is to explicitly force your model and your variables onto CUDA by running .CUDA, like just model.CUDA, data.CUDA, labels.CUDA. What this will do is it will force your labels onto CUDA, and if that doesn't work, it won't let your training even start. So you won't figure out after an hour that your model was slow. You'll figure it out right away. Again, this is like not preferred coding practice at all. Using the .2 command is preferred coding practice. But if you find your model is running slow, you could try this to just ensure that it's running on CUDA. Okay. So training errors. So for this sort of error, your loss does decrease, but it doesn't really decrease enough. And if you're seeing something that is like really low training performance, it's probably going to be some sort of a coding error. But And like, and okay, so here's a important tip that maybe not all of you all know. Whenever you start training any sort of classification model and you're training it with the cross entropy loss, your loss will always start from about the natural log of the number of classes. I said this statement. Can anyone tell me why? Any guesses? Do some quick maths, maybe. Come on, someone. Take a guess. Like, you don't have to be right. It doesn't hurt to try. Sure, he hasn't spoken as yet. Yeah, go ahead. Beautiful, exactly. So, so what he just said was that the loss at the beginning is approximately uniformly random. So the probability of each class occurring is 1 by the number of classes. If your weights are completely randomly initialized, you'd want that to be the case, right? And so if you remember in your softmax cross entropy loss, you have 1 multiplied by the log probability of the corresponding to the class that was predicted. And in the beginning, that will be equal probability for all of the classes. So this comes from right there. This is a pretty, like, it seems like a dumb thing, like, but it's super important in the sense that if this isn't happening, then something is wrong. So this is a good sanity check to check whether, you know, like, you're doing things right. And of course, this is loss averaged by batch. If you take the sum across all of your batches, don't come to my office hours and then like shout at me that you said the loss would start at 2.3, but my loss starts at 200. It's probably because you're not doing averaging or something of the sort. Yeah. So yeah, some different training errors could possibly be like modelization errors, where your model is either too simple to learn, like learn the patterns that are required. It doesn't have enough context, or sometimes your model is even too big, in which case your model will start overfitting. Optimization issues are basically when your model isn't training well. So one very simple example of an optimization error that can happen to you all, like if you try writing the code by yourself and don't just copy paste the code from the recitations, is that you forget to call something like zero grads, or you forget to call the step function or something like that. If you don't call zero grads, your gradients from all of the previous updates will keep getting accumulated, and at some point they might either, till some point it will work as though you had momentum in that direction, but after that you won't be able to train anything at all because it's not decaying. Okay. So, okay, I have a quick question again to like just test you all. Say you're using, as the loss function, you're using cross entropy loss, which I hope all of you all are using for homework 1 part 2. Like, if you all are using mean square error, please stop. Please use cross entropy, it will be faster to train. But say you're using cross entropy loss, and well, in that case, do I use a softmax at the last layer in my sequential model or not when I'm training things on PyTorch? Anyone? You don't use it. Why don't we use it?
Because it's already, well, as far as I know, like that criterion already takes care of the software.
Exactly. So this is some. So what he said was that the criterion takes care of the fact that your logits are essentially unnormalized, and it normalizes them for you using softmax. So if you don't take care of this, and you know you're like, well, cross entropy loss, it should just compute the cross entropy. I passed the normalized logits. My model just doesn't train. This is it's important to read the documentation for each and every part of PyTorch that you are using. And don't read it by read it, I don't mean just skim over it. You're like, well, it says linear, I wanted a linear layer, seems fine. Read each and every parameter in there. It can give you great insight into what different configuration options you have. It will many times give you different ideas about new things you can try to make your model better. And if you would read the description for cross entropy loss, you'll never run into this problem of normalizing the logits before passing them into the loss function. Okay. So I've mentioned overfitting over here. Can anyone quickly tell me how to detect overfitting? What is overfitting and how to detect overfitting? Come on, quick.
It's when you are training models
Mm-hmm.
Too closely approximates the training data, so it can't generalize to other data sets. And
Mm-hmm.
you can tell it's doing that if your training loss is always decreasing, but your validation loss is increasing or plateauing.
Perfect. I couldn't have said it better myself. So what he said was that overfitting is what happens is when is something that happens when your model learns to basically predict the training data very well, but it doesn't generalize very well to testing data. And a very quick way that you can find out that this is happening is that your training loss keeps decreasing. At times it can even go down to 0, right? In that case, your model has completely memorized the training data set, but your testing loss isn't decreasing anymore. And we'll see exactly how we can plot curves and like figure out different ways to visually see overfitting. Like, we don't want to be like, running in the dark with this. Okay. So modelization or optimization issues is a sign that you have one of these is that your training loss doesn't go down well enough. So we know for a fact, as he said, that if you have a powerful enough model and you train it for long enough, your model should overfit the data, which means your training loss for it should go down to 0. We're going to exploit this fact to just ensure that our entire training regime works well, at least for a small set of data. This is a simple sanity check that all of you all should implement before trying to test on the whole data set for any kind of neural network problems that you'll do in the future. What you want to do is take like just one batch or 2-3 batches of your training data and limit your data loader to just that much data. Now, let your model train over this data for many epochs, like it may take a while, but ensure that your model is able to memorize these few batches and get its training loss down to 0. If this is not happening, there is an error somewhere in your training code, wherein you're either like not calling the step function or 0 grads or something of the sort. So this is a very great tool to diagnose whether you've written your training loop well or not. Okay. So a question that comes up very, very often is that, is my model large enough? Is my model too large? And it's, so of course, like one way to figure out whether it's too large or not is to ask TS. But ideally you want to do all of these things by yourself, right? So the way everyone will tell you is you will learn it from experience, but you all have no experience. So where does this come from? So the way you do this is you either start looking at literature to figure out what kind of model architectures people are using, what are the common like filter sizes, or that will come up in CNNs, but what are the common number of neurons in each layers, what should be the depth of MLPs and such. If you're still not able to find any relevant papers in literature, or you're not able to figure out how exactly you want to do these things, you want to just start building slowly, just add a couple of layers at a time and make sure that everything works well. Yeah. So if you feel like you don't have a modelization issue, your model is big enough, so we can start looking for optimization issues. So okay, very quickly, like Bhiksha's covered most of these things in class. If your learning rate is too small, you'll learn very slowly. If it's too large, your loss will diverge. So some default good learning rates are, you can always find the default good learning rates in the PyTorch documentation or in relevant papers. I've just written down a few of them here. For Adam, it's 1e minus 3. A default good optimizer is Adam. If you don't know what you're doing, just use Adam and pray to God, and usually that will just work out. So default weight initialization is the Xavier weight initialization. There are some of you who might be wondering what is weight initialization. Please Google, please look at the PyTorch documentation. So it's important actually, weight initialization, and if you don't know what weight initialization you're using, you really should go to the PyTorch documentation for that particular layer which has trainable parameters. Over there somewhere near where the that module is defined, it will say source. Click on it. Don't get scared when you see the source code. Keep scrolling through it. At some point you'll be able to see the point where the model's parameters are defined, and there will be a reset parameters function or something within there. Over there you can find out exactly what initialization each module is using. You can change this weight initialization according to some new tips or tricks you find in research papers. Batch sizes. We had someone on Piazza who had a batch size of 10,000. It's not a great idea. It's going to take forever to run, probably won't fit on your GPU. SGD and ADAM and all these sort of things work well for your default learning rates that you've heard of, from batch sizes from up to 32 to say like 512. I'm not saying that larger batches don't work. Don't send me links to research papers later saying Facebook did this research and they figured out that you can use a batch size of 10,000 or 20,000. You can, but you need to figure out how to scale the other hyperparameters in a similar fashion. Yeah.
So that's independently from the amount of training samples that you have?
So the batch size, yeah, exactly.
It doesn't have any direct relation with the amount of data.
It doesn't really. If you had a large amount of data, you could probably get away with a bigger batch size. So having smaller batch size essentially gives you more variability in your data. So it increases the variance in your gradients, and increasing the variance in your gradient helps you to basically like go through the loss. The loss function is very diverse, right? And you won't go to more interesting regions if your gradient doesn't have a lot of variability. But if you have a smaller batch size, what ends up happening is that your gradient steps aren't always locally optimal, and that sometimes ends up helping you because you end up exploring the loss landscape more. So yeah, I need to start going through these things a bit more quickly. Please do learning rate decay, look at the PyTorch documents for the documentation for this. Yes? Xavier is a good initialization. It's an initialization scheme. So it's a way to decide, so the weights in your neural network, the weights and the biases, either you can have them Gaussian distributed or uniformly distributed and such. So Xavier is another such technique. You can Google it to find out exactly what it does. It is, everything is in PyTorch, yes. Yeah, so of course one more big optimization problem is if you have a 20-layer MLP that you're trying to train for this homework, and you try to do a backward pass, God help you, because the gradients are not going to reach the very first layer in most of the situations. Your gradients are going to die out and you're going to have the vanishing gradient problem. So ensure that if you're using deep models that you're checking that the gradients are not going to zero, and we'll see how to do that. Overfitting. Again, we talked about overfitting earlier. Training loss decreases, validation loss doesn't decrease. Please do not ever train without also plotting or without also like having your validation loss printed out or something over there. I don't want any of you all coming to office hours saying that this is my training loss, tell me what's wrong. It's impossible to say without also having the validation loss. We will never be able to see whether you're overfitting or not. It's useless. So make sure that you are also printing your validation loss. Make sure you shuffle your training data. If you feel like your model is overfitting, reduce your model size or depth, reduce its capacity so that it's not overfitting to the data anymore, and use one of these many regularization tricks. Dropout, batch norm, I don't know whether it's exactly regularization, probably not, but it helps. Early stopping, weight decay, I can't go through all of these and exactly what they are, but please have a look at the slides later, Google them, it's all a part of PyTorch, not very hard to use. Okay, so important thing is, you decide that you want to be number one on Kaggle and you have like 200 submissions in a particular day, right? What happens is, and you pick the best submission and you figure out, normally my validation accuracy was around 61%. I had this one model, somehow I trained it with the same architecture and it got 69% accuracy. This won't really happen, but say it happens, right? And you're like, wow, I cleared the A cutoff, I rock, I'm awesome, and like, I don't know how I did it, but I did it. And if it works, don't question it. Question it if you're doing too many submissions. What might have happened is, by freak chance, you can sometimes overfit to the validation set. You're not explicitly training on the validation set, but it happens that sometimes your validation set is really small, so your predictions align very well for the validation set, and they don't align very well for the testing set. So if you see a freak increase in accuracy and it's unexplainable and it's because of something that you didn't implement by yourself, be careful. Yeah. Okay. Testing or decoding issues. So this is not an important thing for homework 1 or homework 2, but for homework 3 and homework 4 onwards, you'll see what this is, and it's not really important for now. Okay. Now we're going to get into the whole realm of visualization. So how many of you all are currently visualizing things in TensorBoard or drawing graphs? How many of you all have heard of TensorBoard? Okay, at least, okay, we have at least some over here. How many of you all are drawing plots of your training and testing curves? We have like, okay, we have 3 people over here in the house. Everyone else is doing the age-old technique of staring into your terminal and like trying to find the best accuracy. At what epoch did I have the best accuracy? This is all terrible ways to deal with this. Please don't do this. Please start using TensorBoard and learn to visualize your code. We're going to go through some quick ways of how to visualize things and how it might help you, but this is a very extensive field. I would 100% recommend you go and Google this later and see some more tutorials on how to visualize your code, how to visualize different things. You can visualize things you could never imagine. You can visualize the gradients to figure out whether you have a vanishing gradient problem and so many other things. So, okay. So why visualize? So this is to answer what am I learning. So you can compare your validation accuracy and your training accuracy across time. You can very clearly see overfitting when you're plotting things in TensorBoard, or when you're like creating logs or something. What you can also do, which is a thing that people don't often talk about, which is super important, is to compare the accuracy across different runs. So if you just log everything to TensorBoard, you don't have to manually enter into an Excel sheet the accuracy for each and every different run, because it's saved into TensorBoard. And you can just look at all of the logs for all of the experiments at a time. You can superimpose them upon each other and find out how the model loss is falling with time, which had the lowest loss, at what time it had that loss, and so on and so forth. Yeah. And there are a bunch of other things written over here. I really don't have the time to go through all of them. Okay, why visual? Okay, you can basically figure out how well the activation functions are performing. You can figure out whether the dropout rate is too high and all of these things by visualizing also. But in general, the general takeaway is that visualization is the key tool that will help you fine-tune the network for better optimal performance. You will be able to see exactly at which point your network starts overfitting, so you can compare that to previous iterations of your network to see, okay, this means that my model capacity was too high already at this time, so maybe I can reduce it a bit further, maybe I can reduce it, I can try more regularization strategies and so on and so forth. Yeah. Also, a very important tool is when you compare different experiments here, what you're essentially doing is comparing different hyperparameter settings. So you can very easily figure out what settings of hyperparameters are working for this particular problem. So you're not doing like a blind search completely. Like, think about if you had like 4 different hyperparameters with 4 different values, you try to do a grid search, it's 16 different configurations you want to try. You're completely like in big trouble if you try to do a thing like this. Okay. So TensorBoard is a visualization library for TensorFlow that's useful to understanding training runs, tensors, and graphs. We're not going to be using it with TensorFlow. Obviously, we are using PyTorch. TensorBoard also works with PyTorch, but it's developed by Google, ships with TensorFlow. So as I explained, you can plot time series data, where you can plot gradients, you can plot images, you can plot audio data if that's what your model is predicting. You can, I mean by plot I mean just output these things. You can do literally anything over here. If there's any kind of thing you dream of visualizing, you can do it using TensorBoard. I mean, and appropriate coding skills. Okay. So to start TensorBoard, you need to run through all of these steps. I'm not going to cover all of them. They're in the slides. You can check them later. So yeah, once you run TensorBoard, you're going to basically see the screen in your browser when you open the appropriate URL. And so this is like a quick TensorBoard testing script. So you all can go home and try to copy this code and see what it shows you in TensorBoard. So yeah, so I want to quickly like run through a few small things in this code. He is going to go through Zefan is going to go through a small coding example of TensorBoard in a little bit. Maybe I can just run you all through some of the very basics of TensorBoard. At the very core of TensorBoard is this thing called a summary writer. So a summary writer is an object that you will use to write things like your accuracies, your training errors, images, or some other or gradients or things to TensorBoard. So you define it in this particular format where you specify a runs directory. The runs directory is essentially the directory in which all of your TensorBoard files are stored, and then you have a current experiment directory within there. And TensorBoard will automatically create these directories if they don't exist. It's very important that you have different experimental directories for different experiments, or you'll start overwriting previous graphs, and then it will start looking really ugly, and you don't want that to happen. So you can see that we've defined the summary writer using this writer function over there, and then we have this add scalar function. What add scalar lets you do is, so I'm assuming all of you know what scalars are, but like say like some scalars that we'll often plot are say losses and accuracies. So this add scalar function, as with all of the other add functions in TensorBoard, take three main arguments. The first one is essentially what we call the tag or the variable tag. So it starts with a variable group and then a variable name. It's variable group / variable name. So everything in the same group will be grouped close to each other, and everything in the same variable name across different runs can be superimposed across each other. So for example, you have loss / train and loss / test. So the training loss and the testing loss will be next to each other. And for different runs, the training and testing loss can be superimposed upon each other because they will have different experiment directories, and then you can choose which experimental directory you want to show the loss from. And similarly for accuracy. So if you run that code and everything works well, this is like as you saw, this was like a random function over here, so don't get scared looking at this loss. Get scared if this is your training loss at the end of training homework 1 part 2, that's not good. But so as you can see, like I have the under the accuracy tag I have test and train next to each other. Under the loss tag I have test and train next to each other. So you can essentially see these graphs. On the x-axis you have number of iterations. Oh yeah, so I said the three main arguments. The second argument was the value of the variable, and the third argument is the current time index that you have. So this is usually like a global index count. So if you're running through multiple epochs, this would be current number of epochs multiplied by the size of the training data set plus your current offset within the current training data set or something of the sort. And so as you can see on the x-axis, this is that time step that I was talking about, and on the y-axis is the accuracy or the loss or whatever. Yeah. Again, this explains summary writer again. It's exactly what I said earlier. It's the main object that lets you write things to TensorBoard, and yeah. So yeah, you can just go through these slides later. So again, the add functions, the most important one that you're going to be using is add scalar. I don't know whether many of you all will have the enthusiasm to try different ones like add histogram or add gradients. Do try it out. It will be a good fun exercise to see how it works. But yeah, so these add methods essentially are all of the same format. Tag name, variable name, and the third one is time index. Yeah. So this is the TensorBoard UI in general. So over here in the TensorBoard UI, you can see. Can I get my cursor there? Yeah. You can see over here, these are all of the different experimental runs. So if you check or uncheck them over here, you can essentially decide which ones you want to show over here. And so suppose, so one of them maybe corresponds to no batch normalization, one has batch normalization, one has batch normalization with dropout. You can very easily compare what the training and testing accuracies are across time, what the losses are across time, and so on and so forth. And over here on top, you can choose whether you want to display the scalars, which are like your accuracies and such, or your say histograms or images and other things. Again over here, this is just a zoomed in version of this particular graph over here, and wherein it tells you what the exact value is for each particular experiment. And the first one is essentially the variable group name, and then next is the variable name, and so on. So yeah, so this is my last slide. So if you all are super enthusiastic and you all do plot histograms, again, which I hope you all do, you can even people keep saying in class and like in other deep learning lectures, you might have heard of vanishing gradients, and that if you use a big deep sig model based network, your gradients will vanish. You can actually visualize these things. It's not just stuff that people say and you can never really figure that out by yourself. Over here you can see that this is a sig model based network over here. The gradient weights are of order -3 as compared to tan-H and ReLU, where it's of order of -2. That's why we say that often the sigmoids die out very easily. And if you feel like your model parameters are not updating or something of the sort, you can very quickly come and just check the histograms and see whether your gradients are vanishing or not. So that's all for me. Zefan is going to run you all through some coding examples of TensorBoard. Yeah. Oh yeah, sorry.
Alright, so I'll just go through this notebook to show you an example to how to use the TensorBoard for visualization. And in this notebook, we'll give you an example to train 3 neural networks with different activation functions. So basically, we would like to visualize the gradient of each activation function and compare the gradient. So as we know that the sigmoid activation function is very easy to saturate or die, which means if you have a very large input to the sigmoid activation functions, you will have a very small derivatives. And also if your input is really large and you also have a very small derivative. So here we just want to visualize the behavior of the sigmoid. And before we start, we just install the required libraries. Just make sure you are on the latest version of PyTorch, because if you are in the old version, you might not be able to use the PyTorch. You can just use the third-party TensorBoard X, such like that. And here, note that here we also install the library future. That is a library that TensorBoard depends on. So just make sure you also install that. And the TQDM is another library to visualize your training progress, and it is also a very useful tool. All right, so we just import the modules of PyTorch as usual. So here is how we generate the training data, basically the input and the label. Here is how we build our models. So in this example, we'll just use the MLP with 2 layers. But as I mentioned, we will change the activation functions. We will compare the sigmoid with ReLU and 10H. And we mentioned that if we want to use the TensorBoard, we have to import the summary writer. The summary writer will write your data into the TensorBoard, and you can visualize the data that you write on the TensorBoard. This is how you open the TensorBoard. Type this in the terminal and visit the localhost 6006 on your browser. So this part is actually the training of our MLP. As I said, we will use the TQDM to visualize the training progress of our visualize the training progress. So in the for loop statement, we will just call the TQDM and URL set. So it will show a progress bar when you do the training. Here we call the writer.addHistogram, and this method actually will write the data to TensorBoard and plot a histogram for us. And in this case, we are use the for loop to iterate through all the parameters in the model and write the gradient of the parameters to the TensorBoard. Since we want to visualize the gradient of weights and biases, so the first input parameter is just the name of our plot, and the second parameter would be our actual data, that is the gradient of the parameter, and the third one is number of epochs. That is basically the x-axis of your plot. So we have another example of called x-scalars. This method basically plots a line with multiple variables, and here we just want to visualize the training accuracy and loss, and also with the validation loss and accuracy. The same thing here. The first parameter is the name of a plot. The second would be the actual value that you want to plot with, and the third one would be the x-axis. Here is the number of epochs. So let's just review the activation functions here. The sigmoid, actually the range of sigmoid is between 0 and 1, and as I said, a sigmoid easily dies or saturates, and that means a value too small kills the gradient flow, whereas a value too big saturates the neurons. And they both means that the derivative of sigmoid will become very, very small if your input is very large or very small. And this will cause the backward propagation to passing no much useful information, because your gradient will become very small if you times a value that less than 1 throughout the layer. And for 10H, it is better than sigmoid, but also have the saturate problem. And for ReLU, since the derivative is constant, we don't have the saturation problems. So you may see that the ReLU will converge fast because the gradient of ReLU would be larger than 10H and sigmoid would converge slowest, and that's because the gradient of sigmoid is easily to die. All right, this is the actual training here, As I mentioned, we use the TQDM library, so we can visualize the training progress here. So we use the summary writer in the train functions, and if we run this, the data will be written to the TensorBoard. So let's see what happened on TensorBoard. So basically, here is the plot of the accuracy with respect to number of epochs. And you can see here, the sigmoid actually converge slower than ReLU and 10H, and the ReLU converge the fastest. And if you see the loss, also the sigmoid loss will decreases slowest. And here the 10H is in the middle, and the ReLU will decrease fastest. And here you can change the plot that you want. This is the distribution that a histogram that we plot for the gradient of the model. As we mentioned, the gradient of sigmoid will be smaller than ReLU and 10H. So the red one is the sigmoid, and you can see that the gradient is e to the negative third power, which is significantly smaller than the ReLU and 10H. And that shows the sigmoid can have some gradient vanishing problems. And you may, the gradient vanishing problem, this will be discovered, this will be discussed in later lecture when we talk about the LSTM. And here you just need to know that the sigmoid derivative can easily be very small. So in notebook, we also have this plot. You can also check with that. And the gradient plot of the different activation functions. So that's all. Do you have any questions? It's all right. Oh, yeah.
Back up where you started using the TQDM, there was a for loop that you started using it. Yeah. Could you explain that?
Oh, basically just call the TQDM so in this position, that'll be fine. Yeah.